Alright, we're looking at question 10 from the 2012 exam. So in this question we're asked just to write down the dual of the following LP problem. And we're also given a nice note here saying that we don't have to solve this LP problem. Okay, firstly, I'm going to pop the definition of the dual to the side here. And then we'll use this firstly to explain how to do this problem. And then later on, I'll explain how you don't quite have to use this definition to a T just to save some time, but it is useful definitely to explain the problem for the moment. So I'll pop that up there now. Okay, so here's the definition of the dual. Okay, and C is the row vector of cost coefficients, which we will outline in a sec and write out properly in a sec. A is a matrix of constraint coefficients, and B is the column vector of resource values. And now AT, BT, and CT are just the transpose of A, B, and C, respectively. And X is your unknown variables. In this case, it'll be the 2x1 matrix XY, and U will be a new set of variables that we'll use for the dual. Okay, so that might have sounded confusing, but it'll be easier once I write out what some of these matrices are in regards to our maximization problem given. But I'll write this definition up first because to give ourselves the dual, we need a set of constraints that have less than or equal to signs rather than greater than or equal to signs here. So let's make this change to the top constraint and the bottom constraint. The second constraint's fine. Okay, so we'll quickly rewrite our first constraint. So we multiply both sides of this inequality by -1. So we have minus x plus 2y is less than or equal to -7. And for the bottom constraint, we have minus 5x minus 8y is less than or equal to 3. And I've quickly rewritten the second constraint just so we have everything in nice columns, so then we can make our matrices fairly easily. Okay, now we have less than or equal to signs for each one of our constraints. We can create our matrices according to this definition up here, and then make the dual fairly easily from that. Okay, so this LP problem written in matrix form will be the following. So we have maximize Z equals 12, 8, xy, where we have C is the 1/2 matrix given by the cost coefficients here for the objective function, and x and y are just our unknown variables, and that'll be subject to the following cost coefficient matrix, which is -1, 2, 3, -4, -5, and -8. Now they're just the coefficients in front of the x and y variables here in the order that you'd imagine. And then we have x and y, which is here, and that's less than or equal to the 3x1 matrix 7, 5, and 3. Okay, so this is our original problem, or primal problem, and now we can quickly go ahead and give ourselves the dual by giving ourselves the transposes of these matrices. So the dual problem is a minimization problem, where y is equal to the transpose of B, which is the transpose of this matrix here, multiplied by our new set of unknown variables, which will be u1, u2, and u3. So these are now the coefficients in front of those three variables for the objective function. So let's write that up. So we have -7 u1 plus 5 u2 plus 3 u3. Notice I haven't set them out in this form and then done the matrix multiplication. I've just skipped a step there, which you can as well, because it's a fairly easy multiplication. And then that'll be subject to the following constraints. So we have AT transpose. We'll just read down these columns to give us our coefficients in front of our U1, U2 and U3. So that'll give us minus U1 plus 3 U2 minus 5 U3, and then we write a greater than or equal to sign, and then we write the first value of our C matrix or C transpose matrix, which will be 12, and that'll be our first constraint. And now our second one, we look at the second column here of this matrix to give us our coefficients. So we have 2U1 minus 4U2 minus 8U3, which is greater than or equal to 8, which is the second value of our C or C transpose matrix. Okay, and finally, and this is 3 marks if you remember it, which you all will, I'm sure, we have to write this out explicitly. So we write out that U1, U2 and U3 are all greater than or equal to 0. Alright, so that's the answer for the dual problem here. Now, just a quick note to finish off. This is all a lot of work, writing out the definition and then writing out the original problem into a matrix form, and then finishing off with this final step. If you want to save yourself a bit of time, and you might be able to do this once you've done a few questions like this. Now, to save you writing everything into a matrix form, we can just have a look at the constraints that we've given ourselves up here, and we'll still write them with less than or equal to signs rather than some with greater than or equal to signs. And then we can just give ourselves the dual by firstly giving ourselves the objective function here by using this column here as the coefficients in front of U1, U2 and U3. And similarly, for the constraints that we give ourselves, the first constraint up here, the coefficients where we got those from are simply the coefficients that are in front of our x's here. So we have the coefficients minus 1, 3 and 5 in front of U1, U2 and U3, give ourselves a greater than or equal to sign, and then grab our last value here from the first coefficient up here in our objective function. That's given here. And finally, we do a similar thing for the second constraint. We take this column here to be the coefficients in front of our variables U1, U2 and U3, and then we take the coefficient in front of the corresponding variable y and pop that at the end here with yet another greater than or equal to sign. And finally, we just remember this from the definition. So if you can do that fairly quickly, it'll save you writing out all of these things and possibly this as well, and will save you some time. So that's something you have to decide, just depending on how much time you have in the exam. Okay, and that's all I wanted to say about this video.